Okie dokie. So this slide isn't really too important because he's basically telling you that if the pKa of a conjugate acid of the base of the nucleophile, base or nucleophile is less than 11, you're most likely going to have an SN1 or an SN2 reaction and not the E1 or E2 counterpart. But this isn't super important because 99% of the time he's going to give you heat or a big bulky base, and you're going to know right off the bat that it's going to be elimination. So I wouldn't worry too much about it. The only reason I would consider memorizing it is because A, he made a slide about it, and B, you guys have a multiple choice exam. So he might put it as like a multiple choice question. But the slide isn't too important. All right, so then he goes on to talk about E2 reactions with cyclohexane. And for E2 to work on a cyclohexane, the leaving group has to be axial to the beta hydrogen that the base is going to be pulling off. So let's look at that. Why does it always do that? Like, literally why? I am sorry. I'm sorry, you could skip over this. Okay, anyway. Back to where we were supposed to be. So to be able to tell if they're anti when they, all right, that's an ugly cyclohexane. So to be able to tell if it's anti when they give you the cyclohexane, you obviously have to draw the chair out, which is pretty repetitive of what we already did last exam. So you guys should be good at this. Ooh, I added an extra carbon there. Okay, so using his example, we'll practice drawing a chair. But like I said, you guys shouldn't have any issues. So just make sure when you make them, if the first one is axial up, the next one has to be axial down. Then the first one has to be the next one has to be axial up, then axial down, then axial up, axial down, etc. Make sure if you draw all of your axial up and downs, you draw the hydrogens in the right places. I'm not going to do it because it's a waste of time. But for an exam, if you don't draw a hydrogen in here, for example, they're going to assume it's a methyl. Alrighty. So, well, you guys have all multiple choice, so I guess it doesn't matter. But anyway, let's go and draw it in. So since they're both on wedges, they both have to be going in the same direction, either up or down. O'Connor prefers to use wedges as up. So I'm going to go on the first carbon and draw my ethyl group going up, and then the corresponding hydrogen going down. And I'm going to go in and put my Cl up, so it's going to be on equatorial, and my hydrogen down. In this case, even though this hydrogen is technically also beta, but your double bond is going to prefer it to be on the more substituted side. So we're only going to worry about here because this is where your double bond is going to want to go. Either way, you can't form it in this conformation because your Cl is on equatorial and it needs to be axial. So the only way we can do that is to do a ring flip or a chair flip so that we can get them to be both axial. Also, okay, just to confirm, these are all the beta hydrogens to Cl. So beta just means one carbon apart. Cool. All right, moving along. So once we do the ring flip, we're going to have the ethyl equatorial and the hydrogen axial, the Cl axial, and the hydrogen equatorial. Now you can do the reaction because this hydrogen, the beta hydrogen, is axial to Cl. So your base can come in. Again, this is an E2 reaction. So your base is going to come in, pull this H off. These electrons are going to move into your ring, and the Cl is going to get kicked off with the formation of a double bond. And that is going to give you this as your product, which is the same as this. So yeah. He makes the point that it's no reaction in this conformation, but you have to do the chair flip, and then you'll get the product that I just showed you over here. His is a little bit sloppier, though. And then he does it a couple more times, but it's pretty easy. And if you guys have any questions, you could always ask me. I think it's relatively straightforward, though, so if you guys did well on this in the first exam, you should do well now. So here he's pretty much summarizing things that we already talked about, that E2 and SN2 are similar to each other, and they both prefer tertiary substrates, and then finally, or like, not finally, but then secondary, most likely not primary. So this isn't really important, just a summary of what's going on. Base strength, strong bases favor E2 reactions. If you're making a chart of E2 versus E1 and then SN1 versus SN2, I would make a chart and like, or maybe take a piece of paper and like divide it into 4 pages or like 4 sections, and then do E2, E1, SN1, SN2, and make sure you know what solvent, what base, what nucleophile, the mechanism, how many steps, is there an inversion, is there a carbocation intermediate with shifts. So he's basically just summarizing factors I already told you. So strong bases favor E2 reactions. And then he goes in with the halides. Yeah, honestly, SN1 and E1 always compete, but you know, he always favors elimination. This is all really repetitive. Like, there's really nothing new in these slides. He's just trying to make a chart for you to keep things organized. Okay, so this is something new, dehydration of alcohol. Okay, so for dehydration of alcohols, the most important thing you're going to want to do is add this reaction to your sheet. And this is the dehydration reaction. So you start off with an alcohol, use H2SO4 over H3PO4, and you're going to end up with the more substituted double bond as your major product. I was going to find another example of the mech, but I genuinely have looked everywhere, and O'Connor seems to be the only person that thinks the mech occurs this way, and I can't even find another one in his notes. So I guess we're just going to go through his notes together. Okay, so the first step of his mech is that the lone pairs from the OH are going to pull off an H from the sulfuric acid, which is H2SO4. And then you're going to be left with the protonated protonated OH, so like water basically. And as I made the point before, this is a really good leaving group, so that's most likely why we protonated it. And then it's going to pop off following an E1 reaction. So if it's following an E1 reaction, we know the next step is going to be that the base is going to pull off the beta hydrogen. In this case, it doesn't matter whether it's this one or this one because they're both equivalent. So in our next step, we do see that the base, which is water in this case, pulls off the beta hydrogen to the carbocation. And when it pulls it off, the electrons that were bonded to the H are moving now into the molecule, forming the double bond. And because we pulled this H off and there was no leaving group in this situation, we're fine. Doesn't have to be anti-periplanar. This is not an E2 reaction. This is E1. However, this reaction also does work with E2 reactions. If you were to use a primary alcohol, you can use the same reaction. And he shows that mech. Basically, you use H2SO4 as your first step to protonate it. And this part isn't part of your E2 reaction per se, because normally in an E2 you don't need to protonate anything. So this technically isn't E2 right here, but the E2 starts after you protonate it, which is this step, because the base is going to pull off the H, and that in one step is going to move down and kick off the good leaving group, which is now water. So this is the E2, and this is the prep step, I would call it. I wouldn't waste time memorizing these mechs because, like I said, I can't even find another one. I don't think he would ask it to you guys unless he talks about it in office hours or makes a big deal out of it. This would be really new for him to put on an exam. But I would definitely make sure you know this reaction by heart because he'll probably put this in a box problem. It's a very, very, very common reaction. Okay, so then he brings up the point of rearrangements, and this is kind of what we did last time with the SN2 and SN1 reactions. when you're doing an SN1, you have the carbocation in intermediate. So of course you're going to have the risk of rearrangements. And this is exactly what we did last time with ring expansion. So if you guys want me to, I can make a video to go over this like again. But I personally feel like we already did this. So yeah, I don't know. I just don't feel the need. So I'll go through what his mechanism is though. So in the first case, he uses acid, which means it's going to protonate this and make it a good leaving group because now it's water. So after it pops off, you're going to have the carbocation left behind. But because there's two methyls here, you're actually going to have a methyl shift in this situation. Reason being is that there's no hydrogen to shift. It's always going to prefer to shift a hydrogen before a methyl because a hydrogen is smaller. So now that we don't have a hydrogen, this methyl is going to shift over, and the new carbocation is going to be on this carbon. And we do see that in the next step that the new carbocation is here, and the methyl has shifted over from here to here. Okay, so now you can have your two mixtures of products because you could either have, let me erase, you could either have this hydrogen getting pulled off, or you could have this hydrogen get pulled off, or you could even have this hydrogen get pulled off. As long as it's a beta hydrogen, any of them can get pulled. In this case, the most substituted one, the major product, is going to be if you pulled off this hydrogen. And that's the one he did, so you'll get the double bond there. And then you have your major product. This is another one that's almost equal. Oh, okay, let me point. So this is your major product, this is this is okay, and then this is your minor down here. Okay, moving on. So the ring expansion, the ring expansion we saw in the other one when you have the carbocation intermediate. So in this case, we're protonating this OH to make it water, which is a good leaving group. So after you protonate it, it's going to leave, and it's going to leave behind a carbocation here. So in this case, because it's a four-membered ring, four-membered is unfavored. So these electrons are going to move over and form the new bond, and the new bond is going to be like this. So I want you guys to practice these on your own, make a couple examples for yourself. I don't really see them on exams that often, but he has done it in both this lecture and the last, so I'm assuming you're going to see a ring expansion question. Just practice with the numbering and see if you can do these on your own. Since we did it last time, I won't go over it unless you guys want me to make up some examples for you. Let me know, and I will totally do that. Okay, moving on. Okay, so this is probably the most common and most, I think, important, most important route to dehydrating alcohols. I apologize. This one is most likely going to be the mechanism that they're going to ask you for. So I would put a really, really, really big star next to this and make sure you know this one really well. So I'm going to, on the next page, go into it with you guys. So what this does basically is, let me explain this in a way that makes more sense. So you won't have the carbocation intermediate in this situation. So this is the way to eliminate any sort of risk of rearrangement. So you're not going to have, if I can get my box to come up here. So you're going to have no carbocation rearrangement. So this makes this one the more preferred way of dehydrating an alcohol. So I'll give you an example mechanism. It's reaction. It's the exact same thing from before. So POCl3 over pyridine. And then you get the more substituted double bond. Okay. So let's give you guys a practice mech. Okay, so say you're starting with this, and you have POCl3 over pyridine. Your answer is going to be this plus the protonated pyridine. I'm going to get to the mech. This is just the overall reaction. Oops. And this is your side product. Okay. So now, starting the mechanism, the first step is going to be, okay, let me draw it out first and then we'll get into it. So this is what the structure of POCl3 looks like in the beginning. So you're going to start, wait, let me give it more space. So the first step, because the P in POCl3 is a electron acceptor, the electrons from your O and your OH are going to attack the P. However, P doesn't want any more bonds than it already has. So in making this new bond, it's going to kick out one of its CLs. So the CL is going to take the electrons with it. And now your product is going to be, oh, this is an irreversible first step, by the way. So now your product is going to be OH plus bonded to the PCl, Cl ketone, and the Cl anion. So this is your first step. Sorry, it's getting a little cluttered. Now your second step is going to involve the pyridine. This is very similar to the MEX for Sokol, SOCl2, and PBr3. They pretty much all do the same thing. They're just trying to avoid carbocation intermediates. The other one's adding halides. This one's making a double bond. But the goal is still to avoid the carbocation intermediate. In general, in orgo, they just do not want any uncertainty. And anytime you have a carbocation, you just aren't 100% sure if there's going to be a rearrangement. So that's why most of the time, these will be preferred reactions. So your lone pair from your N is actually going to deprotonate your molecule. And those electrons are going to return back to the O. Okie dokie. All right, let me hopefully draw this a little smaller. O, P, Cl, Cl, ketone, and then you're going to have the protonated pyridine with a positive charge now on it. Okay, moving on to the third and final step. All of the steps in this reaction are irreversible. So let's go. So now you're going to have another pyridine in solution. And you're going to have your molecule from before. Okay. And what's going to happen is that the pyridine is going to pull off a beta hydrogen. So one away from the carbon that's bonded to the O. So if this is the carbon bonded to the O, we're going to want to move one away. So moving one away is here. So it's going to pull off this hydrogen here. But I'm going to draw that in blue. Okay. So these electrons are going to pull this hydrogen, like I said. And then these electrons are going to return to the molecule. And because this carbon already has two hydrogens on it and doesn't want more than 4 bonds, it's going to kick off the OPCl2 part of the reaction. And this right here is going to form the double bond, by the way, if I didn't make that clear. Okay. So your product is going to be this plus protonated pyridine. You're actually going to have 2 of these by the end of the reaction. So if you want, you could write 2. And then, but for this case, I'm not going to, just because I'm going step by step. And then you're going to have the O minus PCl, Cl ketone. And yeah, that's the mechanism for this. This is really, really important. I would definitely know the mech for this one. He also includes his own mechanism in the notes. I just like giving you guys a different version of the same thing. So zooming out, in case it was unclear, this is the whole mechanism. This is step 1, step 2, step 3. And this is the overall reaction on the top.